Welcome to a presentation on wave interference. I hope this presentation helps kind of put together a few of the things that are associated with interference and helps you with the upcoming problems and lessons. Let's start with a graph of a wave. In this case, what we're going to do is we're going to choose to graph this some sort of a displacement. So this would be like a y displacement, like a physical wave in water or something like this. But we're going to give you a graph of position with respect to time. Remember, this is one of the ways that we can represent a wave mathematically. And then I ask the question is, what does this portion of the wave right here, like right to here, represent on this graph? Think about that for a second. Now, if you would wanted to answer that that's one wavelength, you can be forgiven because visually that looks like one wavelength. But because I've identified this as a graph with respect to time, we're not looking at lengths here, but we're looking at lengths of time. So in this case, that portion of the graph represents one period. In other words, the amount of time that it takes for one full cycle. So on this graph, therefore, you can kind of see that the next full cycle is completed over here at twice the period, or 2t. You can see that the first portion, in other words, let's say just the crest of the wave coming in here, is completed in 1/2 of one period. And so we can continue marking off our graph something like this. And this would be 1 1/2 periods associated with the wave. Now the reason we're doing this is one of the types of wave interference you can get is a wave interference associated with time. And this would be, I guess the best way to do this would be a phase shift, because that's what we're looking at when we're looking at interference, a phase shift in time. And the way it would look like this. You always need two waves for interference. So in this case, we'll call this source 1. Our blue one is our source 1. And what we want to do is add in a second source, a source 2. Now if we said that our source 2 was in phase, meaning we didn't shift it in time, that means at any given moment it's doing the same thing as the first wave. So this would obviously give us something like this. In other words, when the one wave is going up, the other one's going up, displacements are the same, and you get something like this. And that's the classic indication of two waves that are laid over the top of each other, which in interference we would call constructive interference. And the reason for that, of course, is these two amplitudes. For example, at this first location right here, you would add these two amplitudes in some sort of a superposition, and you would get a resulting waveform that looked a little something like this, and we'd call that constructive interference. Okay? So the question would be then, what would happen if we took source 2 and we gave it a phase shift in time by a certain amount? Well, in this case, you can kind of see if I phase shifted in time by 1/2 of one of the periods, you can see what source 2 is going to be doing is it's going to be doing what source 1 is doing 1/2 a period later. And if you look at this location right here, kind of right here, what is the first source doing 1/2 of a period later? Well, it's going down from equilibrium. So that means this thing must be going down from equilibrium, and it's going to follow a pattern something like this. So this is an example of a source that has been time shifted by 1/2 of one period. And now the resultant is destructive interference. Following the same superposition, you can say I would add some sort of a positive displacement at this moment in time. I would add a negative displacement in this time. And you can see that the two waves would cancel each other out, a signal for destructive interference. Now the pattern continues. You can see if I were to time shift my wave by one entire period, then source 2 would be doing what source 1 is doing right here. But of course that means that it would be doing this again, and we're back to constructive interference, a shift of one entire period. Then we can ask the question, what happens if I shift it 1 1/2 periods? It's doing this. which means I come back over here. And you can kind of see this is a common thread in these interference problems, is that there's this repetition of the pattern. So you can kind of see when you're time shifting, if the two sources are shifted by even multiples of the period, then you'll get constructive interference. And if they're shifted by 1/2 multiple, or not really multiples, but 1/2, 1.5, 2.5 times the period, then you'll see there in this case that you'll have destructive interference. And that's how interference works with shifts in time. Now we'll shift gears and we'll represent our wave in the second way that we have talked about how you can represent a wave. And that is, we'll still use this axis as some sort of a displacement. Let's say a y displacement because of a physical wave, maybe a water wave. But then what we want to say is the horizontal axis is some displacement or some distance away from a point. In other words, this is a snapshot, a picture of the wave in space. And then we want to ask ourselves the question, some of the same questions we asked before. What does this represent? In other words, one cycle, what does it represent on this graph? And now you'd be right to say that this represents a single wavelength. In other words, a full cycle of the wave in distance. And so that represents a wavelength, which you use the symbol lambda for. If we continued on here and looked at another full cycle, we could go ahead and count across and mark this as a second wavelength over here. In this case, you can see that this is halfway through the cycle. And when you're looking at distances, the length of the wave itself, of course, that is going to be 1/2 of one wavelength. And then, of course, 1 1.5 wavelength marked out here. Okay. Now we'll call this again the same way we did last time, our first source. For any interference, we need a second source, and so in this case, we'll place it at that same location. We'll indicate some source 2. Now we'll say that source 2 is both of the sources are in phase in time, meaning when one source is on its way up, the other source is on its way up as well. So they're synchronized in time. There's no time shift. So in this case right here, you notice if the two sources, we'll call them like sound speakers or whatever they happen to be, the two sources are located at the same starting point and they're both in phase, then source 2, of course, would look something like this. And that would give us the classic example of, again, constructive interference. But then the question becomes is, what happens if I shift source 2, not in time, but in location? In other words, what happens if I were to place source 2 at this location right here? It's the equivalent of moving a speaker so that one speaker is, let's say, closer to the listener in space. Now the two sources, remember, are synchronized in time. So they're always doing the same thing in time. But now it's separated in space. So source 2, just like source 1, at this time would be going up. And then it would be projecting out a wave that looked a little something like this. And now you can see that everything to the right of the two sources now is going to experience destructive interference because I've shifted now in space. And that's the second type of wave interference. So what we did before is we looked at different patterns in time that you could get interference. In this case, we're looking at a phase shift. Let's say we'll say in distance. You'll see why the term becomes important there, in distance. Let's continue our pattern here. We saw that we could take that second source and move it 1/2 of a wavelength to get destructive interference. Let's move it a full wavelength and put our second source here. Notice that the two sources are doing the same thing. So since this source is on its way up when it starts, our second source has to be on its way up. And you can kind of see that any listener or anybody experiencing this wave that's over in this location over here is going to experience constructive interference from those two waves adding together. And continue the pattern just one more time. We'll take our source 2 and take it to 1.5, like this. Remember, these two are in sync, so therefore this source has to be going up, and you can see the continuation of the wave causing destructive interference. Now what this is showing here is the same sort of a pattern, now not a pattern in time, but a pattern associated with actual physical displacements of the each of the waves. And you can see that this sort of interference in space occurs at different phase shifts. You'll notice you got constructive interference at distance shifts of the second source of multiples of the wavelength itself. So when there was no shift, you had constructive interference. When it was shifted, in other words, it was like this. When you had a shift of one full wavelength, it was like this. When you have of two full wavelengths, it's like this. You'll get constructive. Destructive interference is if the shifts are in half wavelengths. So 1/2 wavelength, 1.5 wavelength, and so on. Now I should mention one thing associated with the math for these problems is the way this is normally shown is the easiest way to do this is to do the, let's see, we'll put the source 2 at this location and show this pattern right here. You notice that this source has been shifted over a certain amount. In other words, the physical objects, let's say the source of your sound, let's say speakers or tapping on a surface of the water, the location has changed. And we give that symbol D. So this is special to the distance, these distance shifts associated with interference, D. And we call that D the path length difference. And the idea is this. The idea is that if you do have let's say a listener or an observer that's over at this location here, you could see that the distance that the sound travels from source to observer is different by the amount of the path length difference. And it turns out this path length difference can give you either one of two results, at least in even amounts. Of course, you can have all kinds of odd amounts in between, but in even amounts, if D is equal to 0 or a wavelength or 2 wavelengths, you know that you're going to have constructive interference at the location of the observer. If D, in other words, these shifts, are equal to 1/2 of a wavelength or 1.5 of the wavelengths. Whoops, I didn't mean to write it that way. Let's go back here. Here we go. 1/2 wavelength. That looks a little better. And 1 1/2 wavelengths and 2 1/2 wavelengths. You can kind of see the pattern. You're going to get destructive interference at those points. Okay, and so that's kind of the mathematics associated with phase shifts causing interference due to distance. Now the last thing I want to talk about, I won't go through the entire math of this, but I want to at least show it because it's what you'll work on next. Once you've figured out these kind of linear examples where I've given these two sources linearly kind of lined up. In this case right here, what I'm going to say is what happens if my source 1 is located here and my source 2 is located here. In other words, I'm shifted now kind of in spatially, like laterally, some distance away. Well, it's pretty clear here that if you have some observer that's out in this location, let's put them back at this location over here, they're going to hear sound from both of the two sources. I'm not going to be very good about this, but I'll do my best and do our sine wave coming from this location here. So the two sources are in phase, so there's no shift associated with time. But you'll notice this is that these two waves do not travel the same distance to get to the observer. if I were to kind of mark this off as a circle here, you could kind of see that speaker 2 or source 2 is this much further away. And that much further away is a D, a path length difference. And so you can have these speakers that are shifted along a line of the observer, but you can also have them shifted off to the side of the observer, in other words, laterally shifted, and it will also create a path length difference. The rules are the same. The path length, if this path length difference, the difference between the observer and the two sources, is equal to even multiples of the wavelength, you'll get constructive interference, and at 1/2 intervals of the wavelength, you'll get destructive interference. Now, hopefully this idea of time shifting to get a phase shift and interference and distance shifting will make sense to you, and you'll be ready for the next step in working interference problems. Thanks a lot for joining me.